record once I get into doing the problems. Okay. So for this one, right, the division, when we have division like this, we want to rewrite it as multiplying by the reciprocal. Does that help with that problem? I didn't.
Yeah.
Okay. There was also a question from the take-home work. Take-home work number 5. And so I'll push that back too until Monday night. So let me do a similar problem here. Say 2x over x plus 5. Sorry, let me change that. I don't like that one. Let's do 2 over 3x minus 6 plus 5 over x minus 4 equals 2x over x squared minus 6x plus 8. Okay, I like this one better. So if you remember our talk from last week, the key thing when we are working with these rational expressions, right, fractions of polynomials, number 1 is to factor. We always want to factor. And then number 2 is to decide which strategy you're going to use for which type of problem. So with this problem, I actually like to think about the strategy even first. This problem is an equation, right? Very clearly an equation, equal sign. And with equations, our goal is to eliminate the denominators. The factoring is going to help us do that, but we want to multiply on both sides of the equation something that's going to cancel out with all of these denominators. In order to make it manageable, I really do have to factor, because otherwise I'm going to have to multiply by like all of these pieces, and it would be a huge giant mess. It's already kind of a mess, right? And when you do these problems, it turns out when you factor, there's a lot of these overlapping factors, right? There's this x minus 2 and this x minus 4 that are shared. So that's going to make it so I don't have to multiply by as much to get to my answer, right? To cancel out those denominators. Let's see if I've got a different color here. Try this. So I'm going to multiply all 3 of these by the same thing. And I need to cancel out the 3, the x minus 2, and the x minus 4, right? And here the x minus 2 and the x minus 4. So I need a 3, an x minus 2, and an x minus 4. And I need to do those to all three pieces. That's because it's an equation. I have the ability to just multiply the tops, right? The numerators. Really, I'm multiplying, by this, which means I just have to multiply the numerators, which really means I get to cancel The 3's cancel and the x minus 2's cancel. So I get a 2 and an x minus 4. Here I get a 5 times a 3, so that's a 15 x minus 2. And here I get a 2x times a 3. That's our goal with equations. I do not want to add these together. You can, but I'll tell you that it just doesn't work out very well for students. Even if you add them together properly, you're still not really solving the equation yet. So you want to get rid of the denominators, then you end up kind of starting over. Like I have no more rational expressions to work with. I can just solve this like it's a regular old equation. Sometimes these will be quadratics and you may have to factor. Sometimes like this, they'll just be linear equations. And x equals 38 and x equals 38 over 11. Moving things around. I do have to be careful that this value does not make any of these denominators 0. If it did, it couldn't be a solution because I can't divide by 0. The only ones I have to worry about is if I got 2 or 4. This is not 2 or 4, so I'm good. It is a solution and is the solution I'm looking for. Questions at all about that problem? That's a decent problem. You have to do a little factoring and a little work. It looks bad in the beginning, but once you do the factoring and the canceling, you're going to end up with an equation that's going to be much more manageable. So you want to make sure you start with that approach. Other questions?
I do.
Great.
So for my lab, it says that so -8f squared g to the 4th, so g 4th, g squared 4th or whatever, like it's four on top.
Okay.
And then over, so divided by, so that basically the whole thing is a negative number instead of saying a -4. So it's the same as -64f squared. And then G5. And then everything is times by G to the 6th.
G to the 6th?
Yeah.
Was this an F or an X here? That's
F squared.
F?
Yeah.
Okay. So I think this is it's just this times G to the 6th.
Yes.
Okay.
Yeah.
So to me, this looks kind of like an exponent problem in that I have these are all factors in the top because there's no addition here, and these are all factors in the bottom. So this case, I can start by canceling some of these common factors, like this f squared on this top and the f squared on the bottom. Those are going to cancel out because they're the same factor on the top and the bottom. That's very different from this kind of expression. So it's important that we notice that you cannot cancel the x squareds here because it's x squared minus 4. It's not a factor of x squared, right? Not x squared times something, but x squared minus something. So this is a different kind of problem. This one I can really divide or simplify these pieces directly. So the -8 and the -64, I can cancel an 8 from both of those, or a -8 from both of those. And then here I can subtract the 4 from the 5, which is going to give me a g to the 1. Right? I can cancel 4 of those g's, and then I'm multiplying by a g to the 6th. So one of those g's is going to cancel, or I can subtract the 1. So it'd be g to the 5 over 8. And the f's and the g's are a little funny. We usually like kind of a's and b's, or maybe x's and y's, but the way that was written or given to us is really reducing using those exponent rules.
Is that 1 divided by 8g? Is that a
Well, it'd be g to the 1. You wouldn't normally write the 1 in there. It's because there's 4 g's on the top and 5 g's on the bottom. So 4 of them cancel, and you end up with just a single g on the
so
bottom.
if it's like g on the top, g on the bottom, and then it's the lower numbers on the top and then the larger numbers on the, do you like minus, are you minusing the 4
Yeah,
from the 5?
yeah, you can do it that way too, definitely. So I'm anytime, like, I could move this +4 on the top down to the bottom. And when I move that, that's what creates the subtraction or the minus. So this would be 5 minus 4, and that gives me the g to the 1. We sometimes move the bottom up to the top, which again makes me subtract this number. I didn't do that in this case because it would have given me g to the -1. It's fine, but I liked it having just the single g on the bottom. X to the 7th over x to the 9th.
So my question is, when you times all of the top number, you have g fifth to the fifth. I thought it was like g to the 6th.
Because like, where did the g to the 6th go?
Yes.
So I took care of that kind of in the second step after I simplified this first expression. I
Okay.
got this 1 over 8 times g
Okay.
times g to the 6th.
Okay. So is it 5 minus 1 since
That's right.
since g is 1? Okay.
That's right. Sorry, it was 6. It started out as a 6. G to the
Okay.
6th. This g to the
So
6th over 8g. So it becomes 6 minus 1, which is g to the 5th.
okay, so you basically multiply across to get g to the 6 over 8g.
That's right. That's right.
Okay.
Yeah, and I mean, when you have fractions, like sometimes, like 2/3 times 7, it's like, well, that whole number you can just write as over 1, and then you can sort of do your multiplying or dividing or whatever you need to do with that. So if you end up with a fraction and sort of a whole number or not a fraction, you can just write it over 1 to help you sort of work with it as a fraction. Okay. Other questions?
Could you do an example problem of the take-home homework question number 5, please?
Yeah, let me take a look at that. Sorry, give me a second here. Page. Yeah, so I mean, number 5 is somewhat similar to the first one that we did. In that it's an equation. And so our goal with that equation is to cancel out the denominators. So here's a slightly different one, but let's make that minus. So I think that the take-home work has 3 terms. This one only has 2 terms. But in either case, I have denominators here, right? This one has an x squared and a 9. So I'm going to need to multiply all of these by a 9x squared. The 0, of course, stays 0. Here the 9's cancel and I get x squared. And here the x squareds cancel and I get 9. So I've gotten rid of the denominators. Now this equation that I ended up with is a quadratic equation because of the x squared. So I'm going to need to solve that one by factoring. You can factor it directly as it is, but you may be more comfortable moving the x squared over and the 9 over to make the x squared positive. This probably looks a little more familiar. And this one turns out to factor and give me my 2 solutions of 3 and minus 3. We again check those back in the original denominators and there's no problem with either of those numbers, right? X squared 0 would be my only problem value. Right? It's never 0. So these are both solutions. Does that give you a little clarity on that one?
Yeah, thanks.
It's slightly different because there's, I think, an x and an x squared in the denominator, but an x squared will cancel both of those. So you'll kind of multiply through and again, turn it into, that last one turns into a quadratic that you can factor. Other questions? Any others? Okay. Let me show you this last section. Which involves some applications. So, you know, we've worked with applications in our other sections as well. They're sort of always at the end after we've learned to solve an equation, then we learn how to see some kind of word type problems that use those same skills. The good things about applications are that it's kind of the same process all the time, right? We define our variables, we come up with an equation, we solve an equation. That was from the beginning and it's all the way through to now. The only difference is that the equations we are going to get are going to look like this, something like this. They're going to be rational equations typically, right, involving rational expressions. So that's really the new part of these. But as always, there's some kind of versions or types that are special to this section. So a lot of the applications that you start off with are going to be what are called proportions. So a proportion looks something like this: x plus 2 over 5 equals x plus 7 over 8. Now, again, this is not really an application problem. There's no sort of real world situation here, but a lot of real world situations do lead to proportions. So an example that you'll see in the homework quite a bit are these similar triangles. So if the triangles all have the same angles, then their corresponding sides are proportional. So this is kind of classically used. This is how people used to measure like really tall trees. If you had a big tree here, and you had let me draw a better picture. Well, I don't know if it's better or not, but you have a tree, the tree casts a shadow on the ground, and you can measure the length of that shadow. And if you have a person, that person also casts a shadow or some object that you know the height of. So if your person is 6 foot tall and the shadow is, it's in the afternoon, let's say, so the shadow is 10 feet, and you measure the tree's shadow here at 84 feet, then the question is, how high is that tree? And it turns out you can answer this question because these are going to be similar triangles. The sun is kind of creating the same angle for both the tree and the person. So their corresponding sides are proportional. So if we set up a comparison, and you can set up lots of different comparisons, but one of them would be 6 over x. So the height of the person to the height of the tree is going to be equal to the person's shadow compared to the tree's shadow. So this is a proportion in the same way that this is a proportion. It's one fraction equals another fraction. And we already know how to solve these, right? We would multiply both sides to clear the denominators. So here I would multiply by my green marker, right? And I'd multiply by 5 times 8. There's no common factors there. So I multiply over here times 5 times 8. Right? And here the 8s would cancel. Here the 5s would cancel. And so what you get is 8 times x plus 2 equals 5 times x plus 7. And so the book and a lot of people love this kind of cross multiplying, which gets you to the same spot. Is it really saving you much work or thinking? I don't actually think so, but if you want to think of it as cross multiplying, that's fine. If you want to think of it as just canceling the denominators, in my mind, that's sort of better because that works for a lot of different situations. Cross multiplying only works for this kind of very special situation where you have one fraction equal another fraction. If it's 2 fractions equal a third fraction, then you can't cross multiply anymore, but you can still think of canceling the denominators. So this one would be 8x plus 16 equals 5x plus 35, a nice linear equation that we can solve. Right? Subtract the 5x and subtract the 16. And we get a value for x. Right? We can do the same thing here with the tree. Again, if you want to, you can get rid of the denominators by cross multiplying. I get 6 times 84 equals 10x. So if I divide by 10, what's that give me? Divide by 2, both of these, that gives me 3 times 84, 240, 252 over 5. Is that 100? No. Makes sense. Oh yeah, it'd be a little shorter than 84. So what is that? 50 and 2/5. Sorry, it's always a good idea. So what I was doing there is thinking like, okay, does that answer make any sense? And I was temporarily worried that it did not make sense, right? Which makes me nervous, as it should make you nervous, right? A lot of students and people and math teachers sometimes just take the answer and move on. But if you think about it, you'll catch some errors sometimes, right? Since I'm being recorded for posterity, I want to make sure I minimize my errors. So 250 divided by 5 is 50. So that's 50 and 2/5. It's hard for me to tell exactly if that's the right height of the tree, but for a 6-foot person, I get a longer shadow. So the height of the tree is certainly less than 84 feet. So something like 50 seems more reasonable. Questions about proportions or solving proportions? One thing that's kind of, I think, is nice about proportions is that you don't have to set up like this exact proportion. As long as both of these fractions are sort of comparing the same things, the proportion is going to work out. So it's quite likely that someone else who did this problem might say, well, the 6-foot person, I could compare that to their shadow. So 6 feet to 10 feet, right? That's the height to the shadow. So the tree, I have to do that same ratio, height to shadow. That would be x over 84. It looks slightly different, but notice once I cross multiply, I'm going to get exactly the same equation there, which is going to give me exactly the same solution. So don't worry too much about how you want to set up the proportion. Just make sure that both of these are doing the same things. You can't go height to shadow and then over here go shadow to height. That's going to give you the wrong information. Right? It's not a correct proportion. Okay. So there are some, I would say, legitimate application problems that involve proportions, right? Like some of these triangle proportions, sometimes like a mixture proportion, you mix this much for that much concrete, how much water do you need for more concrete? Those are proportions. The other type of problem that you will see, there are a couple of these that are work problems. And I know there's some in the video, but on D2L, so you should look at that for another example. But there's a little bit of a specialized equation with the work ones. So we got to show this to you, otherwise you wouldn't know how to quite set them up. And the work ones look something like this. Let's say a fire hose can fill a ice rink in 2 hours. while a garden hose takes 10 hours, right, as the weather changes, right? Start thinking about ice rinks. How long does it take if they work together? And this is how these work problems are. You have two things, two people or two hoses or two conveyor belts that can complete a job in different amounts of time. And then if they work together, the question is how much time does it take them? And it's not a very easy question because it's not always clear, which one of these sort of does which amount of the job, right? The fire hose is obviously going a lot faster and is going to fill more of the rink than the garden hose, but the garden hose helps a little bit. So we would expect, the fire hose takes 2 hours. So if I add the garden hose to that, I would certainly expect something less than 2 hours, but not as fast as 1 hour, right? That would be two fire hoses would be 1 hour. That's pretty easy, right? If they each do the job in 2 hours, then they each do exactly the same amount of the job. And so they just it takes them half as long, right? But the fire hose and the garden hose are working differently. So it's not that clear how we could set up an equation. However, we certainly have some tools to get started. So let's define how long it takes if they work together as T. Right, we always are interested in our variable. And the question is, how much of the job is completed in 1 hour? So that's really the question that's going to lead us to our equation here. The fire hose takes 2 hours to do the rink. So in 1 hour, the fire hose has done exactly half of the rink. So that's hopefully pretty clear. How much has the garden hose done? Well, it takes 10 hours to do fill up the whole ice rink. So in 1 hour, it's only done 1/10 of the job. Right? We assume it does sort of an even amounts over time. And then the question is, okay, how much do they do in 1 hour if they work together? Well, notice what we're doing here. At 1 hour, we just take 1 over the total amount of time, right? 2 hours, 1 over 10. If they work together, the total amount of time is T. So the amount they get done in 1 hour is 1 over T. And when you're looking at the amount they get done together in an hour, that's exactly the amount that the fire hose gets done plus the amount the garden hose gets done. So what you can do then is set up an equation here. 1 over 2 plus 1/10 is going to equal 1 over T. Sometimes you might know how long it takes them together and not know how long one of these takes, right? So your variable could be in different spots. But it turns out this is the equation that you're going to use for these work problems. 1 over the total time plus 1 over the total time of the two individual pieces is going to equal 1 over the total time when they work together. let's solve this for t and see if we get an answer that seems reasonable. Notice the equation we get is a rational equation. So I'm going to multiply every one of these pieces by 10t. I could do 20t, but that's really too big, right? 10t is going to be smaller and easier to work with. Not such a big deal here for this one, but some of the other ones, it can get a little messy. So I get 6t equals 10, or t equals 10/6, which is 5/3, which is 1 2/3. By my sort of estimation, we were going to do better than 2 hours, but the garden hose is pretty slow, so it doesn't actually help us all that much. It takes us 1 2/3 of an hour, so 1 hour and 40 minutes, that'd be. Questions? The good thing about these problems, again, is that this equation is going to be the same kind of model for all of these work problems. And it turns out that that equation is also almost always pretty easy to solve, like we did here. So they're actually pretty good application problems as long as you can remember or write down that equation, right? That'll help you with your solutions and getting those answers right. Okay. Any other questions? Any other problems you want to go over? Okay. Well, I will let you go. I will send out an email here. I'll try and do that right after class. And I will change those due dates till Monday night. But please don't save it till Sunday, right? That's sort of defeating the purpose of the extension, right? So get started tonight, tomorrow, and give yourself some time, because again, as soon as you finish those up, you're going to want to jump into the next section, right? So we can make some progress on that. Okay, so again, I do apologize for any of the confusion. And hopefully we won't have a situation like that in the future, right? So take care, good luck. It's supposed to be pretty cold and miserable, so it's a good time to be inside doing math. So take care, and again, let me know if you have any questions throughout this weekend or into next week, of course.
I just wanted to make sure. So you say the due date for this assignment or this
The whole section. So the homework problems, the quiz, and the take-home work, I'll move all of those to Monday.
okay.
Okay.
Thank you.
Yeah.
Have a good day.
Okay. Thank you. Take care.